First, I want to thank the organizers for everything, but mostly for giving me 1 hour. And then I could say something which is perhaps not a common knowledge, or I hope so. And the content is, first, I will explain the motivation. Then I will be perhaps more technical, try to describe what we could do for the Siddhartha 2 project. And then the third chapter is my work done in the last 2 years. And the motivation is related to examination, and that's the true story. There is a philosophy professor and a student, and professor is asking, is it easy to make a discovery? And the student is stupid and says, I think so. And of course, the professor answers, it's nonsense. 90% of attempts are wrong. That might be true or not, but this story has that continuation because the professor who worked on foundation of mathematics, he was not successful and committed suicide. And the student started research in strange particle physics. So the student was attached loosely to European K- collaboration. That was a kind of loose collaboration of several laboratories, including, of course, Warsaw and London and Dublin were probably the most active. And that was very important for Polish physics because these were times of Cold War and they allowed some part of Polish physics to somehow avoid the isolation which existed there. And you probably are familiar with some names like Danish, Pnieski, or Don Davis. I would like to recall Eric Barop, who was the chairman of this collaboration. And that's him. He was working in various fields in physics, also in the Manhattan Project, but he was leftish. And that's probably why he was interested in collaborating with Eastern Europe, criticized for being leftish. And what I remember is that one day I was told, oh, be ready, tomorrow Eric Barop comes and he will present his discovery. And that was the Barop's discovery. They found a strange system in emulsion. That is sigma minus and proton pair were more correlated than the pairs which usually come from K- neutron proton capture. And I forgot about this meeting and recalled about that only while preparing this seminar. And it took me about 5 days to find the notes, and I still miss the pictures. And what is said in the notes is that they found a peaking of mass at about 2320 MeV. And that perhaps was not very specific. They stressed that the total momentum of that pair was correlated fairly narrowly at 245 MeV over C. And so it was a peak of about 10% of multi-nucleon K- capture, and that made a peak. And they already at that time attributed that to Y, which now is called lambda 1405, a neutron bound state. And then we had some small discussion, and Ziro Koba, who was with us at that time, he was a sort of my guru, he argued that with nuclear wave functions, in particular in oscillator wave function, momentum of the pair, the total momentum, is larger than relative momentum. So that pushes the pair as a whole. And he argued that the likely process is just a part of K- proton neutron going to sigma minus proton. That's probably the way we would see it now. But they, so to say, viewed it as a quasi-bound state. I will not discuss the situation there, but want to stress that the idea that we may have just resonance here attached to a nucleon was already there. And I think the argument of Ziro Koba was accepted, but that was not the main question, not the main point why the search was not followed, because it was a Martian technique, and the Martian technique needed a lot of manpower. The scanners were probably expensive, and they said that they need 2 years to work on it to have enough statistics. And probably they had no manpower, and this was just the end of the story. And these are the notes which I found. And I don't remember exactly the date. It was probably 1937. And they see it clearly as Y neutron quasi-bound state. So that was it. This state was discussed yesterday by Nina Shevchenko. Now, I could send these forgotten notes on request, but figures are still missing. I will search for these. And morale of this story is, don't trust your memory. Keep notes in order. And the other morale is that you have to care for funding agency. And I have no idea who was funding chaonic studies in Great Britain and which way they are funded. But in Poland, it was a bit tricky because these were funded because one of the important physicists was in good relation with the first secretary of Warsaw Communist Party. But that was the time, and that was it. So this K collaboration at the time stressed 2 points. One, essentially, they stressed that K-meson is a tool to study ordinary nucleus, and that this should be, so to say, impressed upon the nuclear physics community, that kaons might be a tool. And the 2 topics which existed at that time were just the question of neutron skin in nuclei. This was hot topic at that time. And this is still a hot topic, as will be discussed by Alexandra Bertelli today. And the other problem was, are there alpha type correlations on nuclear surface? That was the Dennis Wilkinson idea at that time. Again, I think this will be mentioned by Alexandre Bertelli in the context of PUMA experiment, which goes on at CERN now. And what was the story with alpha particles on nuclear surface? The argument of Dennis Wilkinson was the following, that K minus 2 nucleon capture in deuterium is about 2% of the total. The K minus 2 nucleon capture in helium is about 20%. And K minus capture on 2 nucleons at distant surfaces is very large. It is also about 20%. So the conclusion was that alpha structure exists on the nuclear surface. And that was disputed. In fact, there was an alternative picture that K minus in proton forms a quasi-bound state, lambda 1405, on the nuclear surface. And this lambda 1405 may propagate to more dense nuclear regions and meet many more nucleons. And this density of alpha particles is not really necessity to have such high rate of the nucleon capture. And that was a simple estimate at that time. If you make a propagator for lambda 1405 and if you Fourier transform it, then you find a function which shows you what is the distance that this propagation takes place. And at that time, it was found that this distance is about 1 Fermi. So 1 Fermi at the nuclear surface is large enough to go to the center, really, because that is the thickness of the nuclear surface. But now the situation has changed with the numbers which people believed were true at, say, these 25 years ago. The range of propagation was something like that, 1.2 Fermis. But now, apparently, the models of lambda 1405 have changed. So with modern numbers, the propagation range seems to be shorter. So maybe this argument with propagation is only partly true, and that is some sort of a failure, because these studies were not continued. And now there are other indications that alpha particle structures in neutron skin exist in closed shell nuclei. There is a Riken experiment and there are theoretical works. So possibly this topic should be somehow studied again. The other argument for existence of alpha particles on nuclear surface comes from the antiproton absorption on nuclear surface, absorption from antiprotonic atoms. And in fact, if you capture, say, antiproton on a neutron, the initial charge of the total charge of the pion is -1. If you capture antiproton on a proton, the initial charge of pions is 0. And then the pions propagate through the nucleus, and some of these are absorbed, some of these change signs, and the measured distribution is something like that. And these 4 main contributors from -2 to +1 will be used by PUMA experiment to study the neutron skin in radioactive nuclei. But it seems that those extreme cases, Q equal -3 and +2, are possible only when antiproton is captured on strongly correlated nucleons. So that might be alpha particles, perhaps something else. So this topic, which was, so to say, missed by initial chaonic studies, now recovers with antiprotons. And another application stressed by K collaboration was that K mesons test neutron skin. And it was found in the emulsion that if you compare these two processes in heavy emulsion nuclei, then it was found that the number of neutrons to number of protons is something like 0.3, neutron excess. And this work was, so to say, stimulated by Eric Barrock and Don Davies. And I remember their bitter discussion with Hans Bethe, who was, so to say, trying to disprove these numbers. Anyway, these were not continued. Essentially, the problem was that there was a trouble with lambda 1405. It was not clear what is the energy dependence of this ratio. So now we could, in principle, study this again. I don't know on which targets. I don't know it's Siddhartha, so to say, fit to do that. But the problem now, historically, it was undertaken by ionic atoms. And now the most active seems to be the research with antiprotonic atoms. So that is perhaps the end of my historic recollections. And I would want to say some words about studies of nuclear surface in atoms. And these will be technical questions. And then the other topic will be the attempt to extract lambda 1405 from the promised land of Siddhartha II. And the main problems are the following, that the atoms, when you describe atoms by standard folded optical potential, you have, in the simplest case, two parameters. A is somehow related to scattering lengths, and there is a folding range, which is essentially involved a free parameter. It's not very clear what this folding range is. And I will try to comment on the relation of A to the scattering lengths. Is it really the scattering lengths? And what is the folding range in these folded models? Why? Because myself, I, so to say, was trapped by wrong approach here. And so it is sort of, in some cases, my personal failure. So if you discuss the interaction on the nuclear surface, there are several regions which require distinct models. If you are very far away on nuclear surface, that corresponds to upper levels in atomic state. The life is simple because the perturbation theory works. That means Born approximation to the level width, essentially. And everything seems to be fine, provided you know what is the folding range, which is very important here. Now, if you study lower levels, they come deeper to very unpleasant region where we have the slope of nuclear surface. And frankly speaking, the description of that region of the slope is very uncertain. And we see that if we discuss the quasi-bound state. Of course, they are formed, say, cation quasi-bound states or antiproton quasi-bound states. They are formed inside the nucleus, but somehow you have to include and understand the interaction on the surface. And the standard method is a kind of local density approximation, which the nuclear physics with the local density approximation is very unsafe. Perhaps the mesonic interaction is in a better state. But in the difficult region, we meet several difficulties. First, multi-nucleon interaction. They start here. We have correlations, we have slope, and we have something which is called self-consistency, which is perhaps reasonably well settled by nuclear theorists in this region. Self-consistency tells you that the effective interaction in this region, in a way, generates the average potential, for example, for cation, and this average potential should be given by the effective interaction. But in this region, there is a problem, what to do it. And this problem has not been solved. I tried myself and never succeeded. So there are all the difficulties, and one is the range of interaction on the surface. The other difficulty is going to negative energy, and the third difficulty is self-consistency. And now let me discuss folding range and give you an example. These are upper level widths in sigma hyperonic atoms. Sigma hyperonic atoms involve high angular momenta. So you really believe that sigma going to lambda is the main mode of the decay here. And this must be governed by longest range pion exchange, because otherwise the centrifugal barrier for lambda, for sigma, keeps the sigma away. And the range, if you believe Yukawa, should be something like 0.3 Fermi here. However, you have to transfer momentum. And the momentum transfer here is large, something like 400 MeV. So Heisenberg would tell you that the range is 0.5 Fermi, just inverse of the momentum transfer. So who is right? And it turns out that both of them are right. In fact, if you construct the non-local optical potential, which involves actually these 2 points, x prime and x, and involves mixed nucleon density, which is calculated for us by nuclear physicists. This mixed nucleon density is given by the value of density at the center of mass system, and essentially Wigner function, which is momentum distribution of the nucleons at the given Fermi momentum. So if you elaborate this, then you find that the upper width is given by folding with the range given essentially by a sort of Yukawa potential, but with the mass of the pion squared plus momentum transfer squared. So it is very short range. And then it makes a trap because you initially believe that the folding range might be long, and in many cases, with the decays, it is extremely short. And I fell into this trap with testing multi-channel problems, antiprotonic atoms, because we have only a single channel description of antiproton nucleon potentials. And that, if you elaborate the range, that gives wrong answers. So the morale would be that if you wish to describe interaction of the surface, you should use explicit decay channels, whatever it is. In chaotic situation, we have explicit decay channel. In the sigma channel, we also have explicit. The situation with antiprotonic atoms is more difficult because we have no explicit decay states. The absorption to pions is described by very strong optical potential, and the momentum transfer is said to be somehow hidden in the potential. So that is the trap, and in those cases, it's much better to use zero range approximation. And that we learned relatively late, and I think Benoit Loiseau will show some results related to that. Anyway, coming back to sigma atoms, this range stays short and may reasonably explain the experimental upper level widths with relatively small and relatively large angular momentum. So that seems to be the warning, so to say. Now the question is, how do we describe subthreshold scattering amplitude in a multi-channel description? And to do that, we use quasi three-body model for atomic physics. You have, say, orbiting particle interacting with a nucleon, and there is residual body. And in some cases, we may approximate that by a sort of three-body physics and use the experience of Faddeev equations, really. And first point is that neutron is bound, and there is some recoil energy of that system with respect to this one. So in consequence, the energy in the subsystem of neutron and antiproton or kaon is negative. And that is a certain advantage of the antiprotonic atoms in surface studies, because the energy involved in the atomic states, first, they are determined by the binding energy of the neutrons, of the nucleons, and then these are spread by recoil energy of the order of 5 MeV. So those atoms which allow this quasi three-body system may be used as a test to study the subthreshold energy and the scattering amplitude in the subthreshold energy region. But that is possible only in the very lightest nuclei. Of course, in hydrogen, you have zero energy, you have directly scattering lengths. In deuteron, you are at about -7 MeV below the threshold. And it was shown to us by János Révai a long time ago that, in fact, deuteronic atomic states would not tell us much about the lambda 1405 because we need deeper binding. And deeper binding might be obtained with helium-3, helium-4, but also with carbon and other nuclei. In very heavy nuclei, of course, many nucleons contribute, and that picture may break down. So an easy task to study profile of lambda 1405 in the subthreshold region is perturbative level widths. And if you study the perturbative level widths, this is the example of chaonic upper level widths in chaonic 4F levels. And what you see here seems like the slope of lambda 1405 going down. The red point is a special point because it's the largest nucleus, and perturbative treatment is not good enough. It should contain something more than single scattering. I will discuss what this something more means. So we see a slope, and this might be compared to models, and with smaller errors here, with future Siddhartha, we probably could fix the slope here. At this moment, it seems to be the closest to the slope obtained by Chepley and Smakel, but of course the errors are large. In such studies, you have to use external information, which enters on the level of 10, 20%. That is imaginary part of scattering on neutron and the effect of p-wave interaction. That has to be put in extra. Now, the difficult task is to check the real scattering amplitudes below the threshold, or extract the real scattering amplitude below the threshold. And to do that, unfortunately, you need more knowledge. First is that you need somehow to calculate the amplitudes fully of shell. That is in the situation when energy is below the threshold. It represents somehow quasi-bound states, and you have momentum initial and momentum final different and not related to energy. In coordinates, that gives the range. So that would be easy, for example, with kaons, with separable models of the Prague colleagues. In other cases of more complicated models, it requires heavier work, the work which is usually done when solving the deuteron problem. And you need slightly better nuclear physics. That is the mixed nucleon density matrix. And unfortunately, you have to include some nuclear excitation modes. And I will try to show an example how strong these excitation modes are. So the full of shell scattering amplitudes is so to say, a standard object for two-body physics. You calculate the outgoing solution and then calculate the T matrix in momentum space by this way. And that is usually a hard job, unless you have separable approximation. But that's one requirement. And then checking models with, say, separable approximation is easy. You have scattering matrix, which is composed of the range factors and energy dependence. You calculate non-local potentials, but you localize this potential. That is the more or less standard procedure. And you localize it by pressing these form factors into effective Wigner function and range factor, and you end up in the range factor. And again, as in the case of the sigma, which I showed, the range here is twice shorter than the range in the separable potential model. So kaons, we don't mind in kaons. The range is so short that this is practically the delta function. But if we wish to study antiprotons or sigma hyperons, that range is important, but only in the real part. What we tried to do some time ago, and that was a trap, was to use half-of-shell amplitudes. That is the method used in standard nuclear physics. You calculate the T matrix by this equation. Here, that is the pre-wave function, say sinus, and psi is the outgoing solution. You calculate the T matrix, and it works for negative energies, and it has some range inside. And this range is unsafe because it is longer than with the full potential. So it's better to use zero range approximation. In the recent works with antiprotonic atoms, we were more careful and used zero range approximation here, which is certainly much better for the imaginary parts. It's not good enough for real part anyway. So what I will try to do for the last minutes, I will make some propaganda for an alternative description of atomic level. The standard description used by Jerusalem and Pratt colleagues mostly, that is optical potential folded or unfolded, and that is the best way to analyze it globally, to find some general behavior, and also the only way apparently to study heavier nuclei. But with the very light nuclei, Z smaller than 8, and preferably near to closed shell, we can use this quasi three-body problem. And that has the following advantages. First, removes the uncertain self-consistency question at the nuclear surface. It is described there in terms of additional interaction. And then it's fairly easy to sum the multiple scattering series. So the basis of the model is the following. If you scatter, say, pion on two fixed nucleons, Bruckner invented a formula which gives the scattering lengths, say, on pion on two fixed nucleons. And that formula is very simple. A is scattering length of a pion on a nucleon, and That is the denominator, which is a summation of geometric series. In this case, the geometric series is a series of multiple scattering. A is the scattering length, R is the separation between the nucleon, which is the propagator. And this formula sums the multiple scattering lengths even if the geometric series is divergence. And you essentially, with one parameter, A over R, get the solution. And the extension of that is to allow nucleon recoil, and you have to add nucleon-nucleon interaction. And then you have basically two parameters: the average value of the scattering matrix below the threshold instead of scattering lengths, and then Green's function for nucleon-nucleon interaction. And then the expansion may be squeezed into geometric series. And that's an example of how this geometric series looks like. Omega is just second order scattering. You scatter on one nucleon, then propagate freely, scatter on the other nucleon, and so on. And that terms corresponds to scattering on a pair. That is deuteron in that case, and then nucleon-nucleon interacting in between. And we found that this series, only with second order scattering, was checked against Faddeev calculations in the eta deuteron case. And that works on a 1% precision, even in the cases where we are close to quasi-bound state. That means this is close to zero. Oh, sorry. So the conclusion from that is that omega, in this case, is a summation of interaction as done by optical potential. That means you interact on a system which is essentially unperturbed. And here you have a term which excites the system. And if you look into the numbers in S-wave eta case, these are very small numbers, and excitation of the system is comparable to the multiple scattering effect, perhaps less. So the model which we are suggesting is to sum of the scattering, that is optical potential really, and add up some excitation of the system. So for example, if we have kaon, nucleon, and residual system, we first add up multiple scattering on single nucleons, also nucleons which are there. And then in the intermediate states, we add interaction of this nucleon with residual system. And that is to be done in higher angular momentum states. So the expansion should be very fast. And in systems like kaonic helium or kaonic carbon, this quasi-three-body approximation seems to be correct. And we can, so to say, perform such a calculation and add something more funny. And then if we have Siddhartha data with light nuclei, with lower and upper levels, first to check will be Chepley and Smykal separable potential, because that is what we could do easily. And finally, I have, say, 5 minutes. Is it 5 minutes?
Go.
More. Good. And that is the failure 2020, which I, so to say, passed myself. And it is related to a search of sigma plus in gamma states. And the story was the following. Finuda and Amadeus find momenta of sigma plus after K minus absorption in nuclei. And there is a main, so to say, momentum due essentially to K minus, say, proton going to sigma plus pi minus, and a low energy peak. And the question was, what is the origin of this low energy peak? And experienced people from Finuda told us that, oh, that is trivial. These are sigma plus particles which are slowed down in the Chloe target. So they really are outside of the main structure, and we should not worry about that. And as you see here, it's about 5% of the total. So we tried another model, which seemed to be natural, that sigma plus might be produced with zero momenta in the capture process. That means that it is produced in the gamma state. So the idea is the following, that you scatter K on carbon, which is composed of boron and proton. That produces sigma, and some fraction of sigma is trapped into Coulomb barrier here. And the interaction of sigma with nuclei is still in a very uncertain stage. I mean, some people, like Barcelona people, would like to see this sigma plus to be attracted. Attraction is also seen in the final state interaction of sigma plus on nuclei. Now, sigma minus mesons predict or extract a rather repulsive potential. There is no sigma hypernuclei with the exception of hyper sigma helium case. So the interaction here is not known, and there is a chance that it is attractive but produces no bound state, and the gamma state might be formed here. And if you calculate, fix the potential so that you have a gamma state, then you get a low energy peak like here. And now I have to remind you what gamma state is. Gamma state is a state of particle like alpha particle in nuclei, which is trapped by the Coulomb barrier. So it is really an outgoing wave, which is not normalized. So it is very large inside the nucleus and also outside, and drops down by 6, 7 orders of magnitude and then starts oscillating. It's not normalized, so it has to be discussed as a wave packet. And in this particular case, this sigma plus wave packet is long, but not very long. It has the length of 70 Fermis. So the standard way to describe gamma state is to continue calculation of such a state and cut it at some stage, and we cut it. We did cut it. And if the wave function for this gamma state is calculated in this way, you may define the radius of this state. And in carbon, the radius of the carbon is something like 3 Fermis, but the radius of the gamma state is about 10 Fermis. So most of the sigmas, they really are outside the system. So I assume that there is some sense in non-absorptive situation. Just sigma is not absorbed. And then we realized that that's not true. First, there are two questions which I mentioned. One is that the sigma is absorbed. And that's my error here. I underestimated. If you introduce absorption, say, comparable to the absorption which is seen in the final state interactions, or lambda helium hypernucleus, the probability to make a gamma state goes down by 1 or 2 orders. So the peak becomes much smaller. And the other process is what we were told by Finuda people, is that the sigma plus is slowed down in Chloe detector. So my colleagues managed to calculate that. And that is the result. If the initial momentum of the sigma plus after the capture is something like that, then sizable fraction slows down and is kept somewhere in the detector and dies down, and it waits to die there. So if you compare this experimental result of Amadeus with the calculation, you see that the shape here is different, but this area is comparable. So you really cannot say that anything may be extracted from that. But what we realized was that if there is a gamma state and the absorption of sigma plus is sizable, then it would decay mostly to lambda proton and much less through this sub-barrier emission of sigma plus. And now that is very specific decay in sigma, in gamma state, because actually the energy of sigma is very close to 0. It's a fraction of MeV. So the energy is really below the threshold. It consists of neutron binding, and recoil energy. If you calculate the average invariant mass in that system, it is something like 2108 MeV. And the average momentum for the proton is 240. So if we look at the total sample of lambda proton emitted after cation capture, there is a typical multi-nucleon capture and a smaller fraction which is due to essentially single cation capture with final state interactions of sigma which turn to lambda. And what we see here is that there is something here which exactly corresponds to this momentum. And also there seems to be something here at these 240. So it could be due to gamma state and possibly something else, but I was not able to find an alternative explanation here. So the conclusion here is that the gamma state might be there in this sample, but it is statistically uncertain. And that's the end of my story. Thank you.
Thank you very much. Very intriguing talk. Then we have 3 minutes for question.
If I can, obviously my question is related to this last subject, and my curiosity is how you would suggest to proceed with this, because obviously it's intriguing, and if it could be there, and I can't believe, how can we proceed?
Well, first point is to negotiate with you and colleagues. Is it statistically significant? Because the calculation could be done, and that's it, so to say. If you decide that it is statistically significant, then we can continue. And of course, the question is, are there an alternative? And I think the argument which I believe is fairly strong is that that this is below the threshold and corresponding to zero energy sigma. So I found nothing else which could simulate that, but maybe I was not clever enough to search. So the continuation is very much possible.
Yeah. Thank you.
Thank you. Other question? If not, thank you again, Sławomir.
Thank you.
Please unshare the screen. Fine. And the next speaker, Benoit Loiseau. Are you here? Benoit?
Yes, I am here.
Ah, you are fine.
Yes.
Ah, good. Ciao.
Yeah.
So you may start directly searching for baryonia.
Now, is it working or? Sorry.
Fine, perfect.
Perfect. It's working.
Yes, go on.
Good, good. I would like to thank the organizer who have given me the opportunity to pay my tribute to Slavek. I have had the privilege of collaborating with Slavek for over 20 years, and it still goes on. It has been a long, friendly, and fruitful parcours centered on the search on baryonia. An intuition based on a vast knowledge in physics, together with an ability to approach qualitatively the problems, are the most prominent qualities of Slavek. They are certainly the basis on which our common work has been built, notwithstanding his patience to explain and overcome the obstacles whenever they occur. So Slavek, receive my warmest thanks for all you have given me over the years, and let's hopefully go on.
Thank you, Benoit.
Thanks to our colleague, Jean-Pierre Delonder, who helped me in writing this tribute to Slavek. Let me now proceed with a brief account of our common work on the search of baryonia. No. The outline is the following. I will list the collaboration, list the publication following our collaboration. Then the question is where to search for baryonia. Two answers. First, information experiments like the production of photon in the gypside decay. And we will show our model comparing the invariant PV bar mass distribution over the best 3 histogram data. Then the second answer could be is using experiment testing subthreshold energy region. And I will depict our latest analysis of antipotonic hydrogen and helium atoms. Our fruitful collaboration started in the late 90s, being both invited by Thorleif Eriksson at Uppsala. Since then, we have collaborated within the French-Polish IN2P3 copying agreement program. First publication not involving a nucleon anti-nucleon, we derived a pi lambda sigma coupling extracted from hyperonic atoms. Then with Thorleif Eriksson, we worked on a phenomenology called pi minus p scattering length from pionic hydrogen. Publication related to possible nucleon anti-nucleon or baryonia. First, we study the anti-proton-proton channels in gypside decays. Then, with Bruno Elbenich and Michel Lacombe, we derived a Paris NN-bar potential constrained by recent antipotonic hydrogen atom data and N-bar proton total cross-sections, followed by a work with Bruno Elbenich, Jean-Pierre Delonder on the structure of X1835 observed by Bess. Then with our Jerusalem colleagues, Eli Friedman and Abraham Gal, we worked on anti-proton nucleus interaction near threshold from the Paris nucleon anti-nucleon potential. Then the two works I'm going to describe briefly here. With Jean-Pierre Delonder, we study the photon or meson formation in gypside decays in 2p bar p. And last, the extraction of baryonia from the lightest antipotonic atoms. Where to search for nucleon anti-nucleon baryonia? Since the beginning of Lear and era at CERN, nothing was found in the NN-bar interaction because these states are broad due to fast annihilation process, and experiments are confronted with heavy background. Furthermore, the exclusion principle not operative, and there are a large number of partial waves. Then the possibility is to look for specific N-bar states in formation experiment. And Bess found an enhancement, pp bar enhancement close to the threshold in this gypsy decay to photon pp bar. And there the photon and meson gypsy, they have GPC 1 minus. So only the 1s0, 3p1, and 3p0 final state pp bar are allowed in this channel. So we started with a semi-quantitative description of this process with final state dominated by the isoscalar 1s0 partial wave, where the Paris potential has a 52 MeV broad quasi-bond states at 44.8 MeV below threshold. And more recently, we looked again at the study of these decays, in particular, looking at the formation of not only photon, but also omega, phi, and pion. Then the second possibility is the experiment testing subthreshold energy region, and at in particular atomic levels in light atoms. And this is the useful atoms to study bionia are the antiprotonic deuterium and antiprotonic helium. The experimental data exist. They have a simple, relatively simple nuclear structure. So it allows to study the p bar n interaction below threshold, at different energy below threshold. Then I will describe in second part of my talk this the results we have obtained there. To describe the photon production, we used two processes based on a DWBA approach. First of all, a direct emissions of the photon from the gypsy, and then an emission from the baryonic current. So the A diagrams correspond to the bond term, and the B diagrams are the final, we introduce a final state interaction with the S wave half of shell function from Paris N-bar potential. And the gypsy source is described by a phenomenological Gaussian function with a radius. And we found that to represent the data, we need some small energy dependence on this radius with those parameters here. Then the peak found by the Bess is following is shown in the following histogram for the best data. And our model, so the total is represented by the solid line. And then the direct emission, our direct emission finding is the large dashed line with a peak, with the radius, energy dependent radius on the gypsy source. Then the baryon current is a Dutch dot curve. Then a renormalized electric contribution is shown here with a small dashed curves. And finally, the eta C contributions is depicted by a bright Wigner. You can see here that the baryonic current peak is strongly suppressed due to interference between intermediate P bar P and N bar N channels. We have 7 free parameters, normalization of the source function. We have size of the magnetic and electric amplitudes, which are calculated independently for direct emission and baryon current. And we reproduce, we fit on the emission rates for photon and PP bar. And the P wave electric contribution is renormalized. And then we have parameters, one parameters for the Breit-Wigner. And the summary of this work here, so we have, as you have seen, two processes calculated with DWBA, and which allow to reproduce a very sharp peak close to threshold, which is due to this baryonium, which exists in the Paris potential, and it's a quasi-bond state at 4.8 MeV below threshold and 52 MeV wide. And you have also seen a resonance states at 2.170 MeV, which is a sharp resonance in the same partial waves. Second, this emission from baryonic current is not sufficient, so we had to introduce this direct emission model. And because in this emission from baryonic current, there is a reduction, and the outlook of this work, so in the case of the psi2s, there's no peak, and this could be explained by the different infernal structure with the J-psi. So the direct emission will not give a peak in the psi2s formations. One has to realize that the Paris potential fits data only for invariant PP bar mass less than 2.1 GeV. But we need this potential beyond, and apparently it produced reasonable results beyond. And this present approach could be applied with other interaction, like the chiral effective field third order by those authors. And the present work is related, will help in somehow predicting or giving an idea of the J-psi production meson in PP bar reaction on nuclei, P bar on nuclei, which might be studied sooner or later at FAIR. Now, concerning my second presentation, and where we analyze the antipotonic hydrogen and helium atoms. The level and shift of this anti-atomic atom can be expressed in terms of P bar n subthreshold scattering length and volume. And you have seen from previous talk from Slavek this picture of this quasi-three-body system, which we used to calculate those those levels, shift and widths. And here I just outline for the S-wave interaction. So what we derive this P bar n interaction from the Paris model, and we use the following formula where T are given by these expressions, and V n and bar being the Paris potential for negative energy, and so it's half of share, and the psi 0 is the free waves, and the psi is the solution of the Liebman-Schwinger equation, as Slavek told us. And then if the P bar is bound in an atomic orbital, the energy shift of the upper levels can be generated by perturbation theory. And at leading order, we calculate the shift and the width by the following equations, where we have the overlap on the wave function of the struck nucleon 2, and the psi L being the Coulomb atomic wave function at a given of a given momentum L with beta given by this ratio of the residual nucleus and sum of residual nucleus and nucleon mass. So this is where the calculation was performed. And here I show the results for the antipotonic deuterium. So in this table here, I show the shift. So the first numbers for the S wave is that obtained with the 2009 Paris potential. And the number in curly bracket is that obtained with the 1999 Paris potential. So, and the P wave is here for the shift. So you see the latest version of the Paris potential gives attraction, and that's not good when we compare to the data. And the older version gives repulsion for this P wave and is better reproduce the data. The widths are, on the other hand, the widths are better reproduced and with maybe a too strong P wave. And for in both potential for the 99 potential too, although it is smaller, it's maybe slightly too small. So here I give a plot of the subthreshold amplitude generating the 4p3½ hyperfine structure in deuterium with Paris, and you see that the Paris, so I plot here the amplitude for this subthreshold, and you see that the it is strongly dominated by the scattering length in the 3,3p1 wave, which is bound scattering length at which has a quasi-bound state at minus 4.8 MeV. Although, as Slavek showed, the relevant P bar N center of momentum energies used for in the deuterium important are at minus 7.6 MeV. So somehow this graph shows that a downward shift of the resonance position by something like minus 4 MeV or more will strongly reduce the attraction we have here in the shift. So we hope that this should reproduce better the experimental data. And in the case of helium-3 atoms, we have the following table. Again, the P wave has this attraction, which is not good for compared to the data. It's slightly better with the 99 version of the Paris potential in curly bracket is for the shift. The widths are not too bad agreement, although the slightly too large, still slightly too large for the Paris potential. And this is the leading order calculations. We have calculated the higher order correction, and I show the results here. And the change are not very large, but nevertheless, it improves somehow the widths by diminishing the P wave attraction in the Paris 09 and increasing somehow the P wave repulsions, although the S wave repulsion in the Paris 99 has been reduced too. And the T2P widths are again in good agreements and with not bad agreement with the experiment. You note that the contribution of the P wave interaction depends also on the S wave interaction as a result of multiple scattering summation method. For the helium-4, we have the following results. For the 2p shifts, again, the p wave has this bad behavior of attraction in the 2000 version, 2009 version, 09 version of the Paris potential, and also in the 99 versions. So the comparison to the data is not good. The widths, p widths are doing much better in the case of the 09 and not as good in the 99 versions. This is for the leading order calculation. And if we introduce the higher order corrections, we have the following results with somehow, but still not good. There is this cancellation between S and P wave for this Paris 09, and again, also cancellations for the 99 versions. The widths are better agreement. Now, somehow, we also have calculated the ratio of neutron over proton capture rates from atomic states. And this is an order calculation where Slavek did participate. And it can be seen that for the zirconium and the tin atoms, those tin atoms, the ratio is large, showing neutron halos. But there is so this is somehow obtained is with radiochemical experiments, experimental numbers. There is those cases as two normal, this zirconium and tin, but there's anomalous results for the cadmium and the tin 112, and this is due to partly to the separation energy difference for proton and neutron, but an additional explanation could be a fairly narrow n bar quasi-bond states, boosting the pp bar absorption over that of p bar n. And we have calculated this ratio for the for the deuterium and helium-3 and compare them to the experiment, either for the Paris 09 version or the Paris 99. And you can see that those both models reproduce fairly well the deuterium case. And there's better reproduction for helium-3 and helium-4 for the Paris 09 potential compared to the Paris 99. And this experiment are obtained in a bubble chamber. So let me just do some summary on this latest work. And as you can see, this is the study of antiprotonic levels, the powerful methods to study p bar n amplitude below threshold, down up to -40 MeV, as Slavek has shown in the previous talk. And in Paris 209 is dominated, there is the S-wave p bar amplitude which is dominated by a broad 111S0 quasi-bond states. But this gives a strong repulsion levels in the light atom. However, the p-wave attraction is attractive, p-wave are attractive, and the balance with S-wave. Then there is an insert. We have seen that the uncertain position of the quasi-bond states could be left in the if let me see here. Okay, if we study if there are measurements of the 4p3 half fine structures will help this one. And so this 111S0 is not strong enough. However, in Paris 209, there is a quasi-bond state at minus 80 MeV. And this is the data requires a shift to 60 MeV. And then this repulsion will increase. Note that in the medium and heavy atoms, we found that, like in the work done with the Jerusalem colleague, Eli Friedman and Abraham Gal, the higher nuclear density and level shifts far from Born approximation. And there also, they require attraction. This is model, this p-bar and amplitude below threshold requires attractions. And we found that from this 4p32 fine structure, that the 33p1 quasi-bond state should be rather, which is, there is a minus 17 MeV in Paris 99 and minus 0.5 MeV in Paris 09, should be better be located in the minus 11, minus 9 MeV short range, MeV region, I mean, this region, sorry. So, and if you compare those two versions of the potential, somehow the level shift of the Paris 99 are better, but remind that, as I showed in my first talk, the first contribution, the presentation, the Paris 09 fits, which fits n bar p addition, low scattering length from hydrogen, and the capture rates are better. And this will be an advantage for PUMA project at CERN. And also the best enhancements is better reproduced by Paris 09. And to my conclusion, Paris 09 is a good starting point for successful description of atomic bubble chamber and radiochemical data if the p-wave baryon position shifted down by few MeV, plus this deeply bond state pushed by some 20 MeV. So update of this potential model is work is in progress, and many thanks for your attention.
Thank you, Benoit.
Okay.
Thank you very much.